Welcome back. I hope you're rested and ready to finish this off. So what we're going to learn how to do now is write balanced molecular, full ionic, and net ionic equations for our precipitation reactions. So let's look back up at the table, and I've erased some of my highlighting here. And I want to take a look at mixture 2. So writing a balanced molecular equation should actually not be too difficult as long as you did your table right. So what we're going to do is we're going to have our reactants for the balanced molecular equation. We'll have the reactants on the left side of the equation and our products on the right side. So our reactants and their phase will go on the left side, and our products and their phase will go on the right side. So let's start with the first one. So we're going to have barium nitrate and sodium sulfate. I have to remember that. So barium nitrate plus sodium sulfate. And we have to put their phase. I'll change colors for the phase just so it's clear. They're both aqueous, which means they were both dissolved in water. They were salts dissolved in water. There were no solids present in the solution. So those are our two reactants, and our products, let's go back up and look. We ended up with sodium nitrate, aqueous, and barium sulfate, which was the solid. Okay, and I'm going to change color again for the phase because you have to have the phase. It's important. So those are the species present in our precipitation reaction. So now all we have to do is we have to balance it, and I use a different color for balancing. So for balancing, what we want to do is we want to make sure we have the same number of atoms of everything, or I guess molecules when you're talking about the NO3 group, on the left side and on the right side. So if we look at barium, here's barium, left and right. There's one on each side. So I'm going to try to erase the highlighting and not the text. So the barium's already balanced. But if we look at the nitrate, so the nitrate group here on the left side, there are two of them, and on the right side, there's only one. So what we would have to do is we have to put a 2 out front in order to have the same number of nitrate groups on the left as on the right. So I can't put a subscript on the nitrate on the right-hand side of this equation. You have to put the 2 out front. So then if we look at the left side of the equation, we have 2 sodiums because it's Na2, so there already are 2 sodiums. And if you look at the right side now, because we have the 2 out front of the Na, there are 2 sodiums on the right side. I think I mixed up my left and right there, but I'm sure you know what I mean. And then if we're looking at the sulfate group, well, there's one sulfate group on the left and there's one on the right. So now we have a balanced molecular equation. So I just paused the video so that I could erase my highlighting. So what we want to do now, the difference between the balanced molecular equation and the full ionic equation, is that in the full ionic equation, we're representing what is truly happening. So in the balanced molecular equation, we show these ionic species as being, associated with each other. But they're not. They're aqueous. So in reality, they're broken up into cation and anion pairs. So you have Ba2 plus ions and you have NO3 minus ions. And here we have Na plus ions and SO4 2 minus ions. And for the sodium nitrate, we have Na plus cations and NO3 minus anions. The BaSO4, however, because that's a solid species, that's exactly how it is in these. It's not in solution anymore. It's precipitated out to the bottom as a solid. So we don't break anything with an S or solid subscript into cation and anion pairs. As far as identifying the cations and anions, you should have already actually done that in your table. So if you look here in your table, we have the identity of the cations and the identity of the anions. So hopefully you should be all set at this point with knowing what your cations and anions look like. So let's go down here and write our full ionic equation. So what we have is for the barium nitrate, we have Ba2 plus, and then we have NO3 minus. But for the NO3, we don't just have one NO3 group, we have two of them. So we say we have two NO3 groups, which is very different than doing this, NO3 minus 2. That is not the case. We have two separate nitrate groups floating around. So we take the two, if there's a subscript, we bring it out we bring it out front. The only time we leave the subscript in place is when the subscript is like on an oxygen. So if the subscript isn't directly on an oxygen, just know you're going to be bringing it out front. So then I'm going to erase this. For the sodium sulfate, we have two Na pluses. Okay, that subscript, it's not on an oxygen, so we're going to bring it out front. Plus an SO4 2 minus. That subscript before, it's on an oxygen, so we're going to leave it in place. The SO4, those are oxygens covalently bound to sulfate. That's very different than the sodiums. They're not covalently bound to each other. So what you have in solution is you have a sodium floating around and another sodium floating around, and then you have a sulfur with four oxygens covalently bound to it, floating around as one group. So that's why we keep all of those together. So let's get our phases on there. So this is important. So all of these guys are aqueous. And then we're going to go over to the right side of the equation, which we have two sodiums plus two nitrates plus our solid, BaSO4. And I'm going to put the phases on, AQ, AQ, and S. So there you have it. There is your full ionic equation. So again, the only difference between the full ionic equation and the balanced molecular equation is anything with an AQ subscript is broken up into cation and anion pairs. So the last thing you have to do is just go ahead and write the net ionic equation. This should be the easiest step. So for the net ionic equation, what the net ionic equation does is it only considers the ions that go to form your solid. So I'm trying to underline BaSO4, which is our solid. And to make BaSO4, we need the SO4 group and we need the Ba. So the net ionic equation is simply Ba2 plus, aqueous, I'm going to keep the same color here, plus SO4 2 minus, aqueous, goes to form BaSO4 solid. So what the net ionic equation does is it's showing us what we need to make our solid. That's all the net ionic equation does. Some people like to think of it when the difference between the full and the net ionic equation is that with the net ionic equation, you're losing the spectator ions. So look, I'm realizing I'm missing a minus sign here on our full ionic equation. So our spectator ions are the things that are the same on the left side and on the right. So NO3, we have two NO3 groups. So if we were to remove the NO3 groups and we were to remove the Na plus cations, because they're the same in the left and on the right also, you'd be left with the exact same thing. Ba2 plus SO4 2 minus goes to form barium sulfate. So again, these guys are called spectator ions. And the reason they're called spectator ions is because they're not participating in the reaction. They're just hanging out, they're watching what's going on, but there's no participation. So that's why they are called spectator ions. So what you need to do now is you need to write these full ionic, net ionic, and balanced molecular equations. I just said that out of order, but that's all right. For mixtures 1 through 8. So some of these reactions are going to have, or I should say most of them will have one solid species and one aqueous species. One of the reactions is going to have two aqueous species, and one of the reactions is going to have two solid species. So just be ready to handle that when you're writing your full ionic and net ionic equations. And for more support, interactive video 8.1 in the lab manual actually shows you how to write these equations for mixture 1, but I would try it on your own first and then watch the video and see if you did it correctly. There's a written example for something that isn't one of the mixtures in the calculation sections of your lab manual. And I'm also going to post a link to a crash course chemistry video on precipitation reactions that I particularly like. It's pretty entertaining. So again, here's interactive 8.1 in the upper left. Shows you how to do mixture 1. And here is just another reaction that you could practice with. So I would maybe try it on your own and then go ahead and just follow the written instructions and see if you did it correctly. But I think you're going to be in pretty good shape at this point. So just a few notes about the lab report. The lab report is due by 11:59 p.m. on Friday, April 17th. So you have 2 weeks for this one. You need to have the experimental goal, the precipitation table. You need 8 balanced molecular, full ionic, and net ionic equations. Now I say 8, but there's a couple reactions where you may not have to create the net ionic equations. So if you find you don't need them, that's okay. And you do not need a results table or a discussion for this lab. Do remember that you have to take the quiz online on Blackboard by 2 o'clock on Wednesday, April 15th. That's immediately before our next lab group meetings, which will be on April 15th and 16th. There are no meetings the week of April 8th and 9th because of we're closed for Easter starting on the Thursday. Okay, so thank you. And don't forget, I do have office hours. So if you have any questions, feel free to stop in and visit me online.
So, since I started making these videos the other day, I found some more at-home precipitation reactions you can do, and I'm going to post instructions on these online on Blackboard. But before we use, remember, baking soda and our pickle crisp. So, that was kind of a slow precipitation reaction, and that's because baking soda, it's sodium bicarbonate, which is NaHCO3, and that reacts with the calcium chloride, which is the pickle crisp. But the problem is first, you have to take the bicarbonate ion, which is HCO3 minus, and it has to be made into CO3 2 minus, which is carbonate. So that takes a little while, so that's why that was slow. So, found this other stuff called washing soda. It's in the laundry detergent aisle, and it turns out you can actually use it to make laundry detergent. So, it was like the only thing left in the grocery store right now because all the laundry detergent's sold out. But if we all get desperate, just know you can go online and find out how to make laundry detergent using this stuff. And it's cheap. So anyhow, washing soda is sodium carbonate. So we don't have to make the carbonate. It's already there. CO3 2 minus is present immediately. So I'll show you what happens if we mix washing soda with our pickle crisp. So here, which is our calcium chloride. So this will be a much faster reaction than what we saw the other day. So let's do, it's gonna be a little messy because I'm trying to pour. Washing soda, pickle crisp. See, so it's turning white. There we go, we need a little more. So the calcium carbonate is produced really quickly from this reaction because the carbonate doesn't have to be made, it's already available. The other thing we can do is we can mix our washing soda, our sodium carbonate, with Epsom salt, which is magnesium sulfate. You can get that, it's cheap. You can get it in any drugstore. And so watch this one. Washing soda, sodium carbonate with Epsom salt. Whew, there it is, precipitation reaction. So this one is magnesium carbonate that's forming, and this one is the calcium carbonate. So I will post these recipes online, and maybe you can try some of these out at home. I just want to say happy Easter, everybody. Also, in my family, we've always done this decorating of an Easter egg tree, we call it. It's just different flowering branches. So I have pussy willows and peach blossoms. And I've just started decorating, trying to bring a little color into our lives here. Cheer us up a little, because I know this is tough on everyone. But hopefully you can get out and find a way to get a little color back into your life. So happy Easter.